what we use this for. Okay? So most of the time, we just give the solutions from 0 to 2 pi. Now, here's where we really need this. We need this idea here when we have coefficients on our angle. Okay? Now, on this one, the directions here, I'm not going to say name them, name all the solutions. I'm only going to go back to say, name the solutions only that go from 0 to 2 pi. Okay? Now, let's look at this though. Look how this is different and see if you can kind of follow what I'm saying here. All right, what's something there that you hadn't seen yet? Yeah, the 2 in front of the angle, right? So we call that number a coefficient. All right, now he kind of makes life difficult a little bit. Not so much difficult, it just makes the problem a lot longer, okay? Because you got to do a lot more work here. Now, the idea is, okay, so be sure you write this down, all right? Because of the, I'm going to say COE for coefficient, okay? You must name the general solutions first. Okay, so because you have a coefficient on your theta angle there, what you have to do is you have to give the general solutions. And when I say general solutions, I mean that formula thing, the plus 2 pi k thing. Okay, now, so let's see. Now you don't divide the 2 off. Now, if I had a 2 in front right here, I could divide it off if I needed to. All right, but we just look and we just ask the same old question: where is cosine negative 1/2? All right, that would be in the third and fourth. And I believe that would be 4 pi over 3. Am I right? No, oh, I'm sorry. I said that's wrong. It would be in the second and third. All right, so it would be what? 2 pi over 3. Am I right? All right, so, all right, 2 pi over 3 and 4 pi over 3. Now, what's different here is I'm not going to say theta equals that, but 2 theta equals that. So 2 theta equals. All right. Now, right. So even though it only asked me to go from 0 to 2 pi, because I have a leading coefficient, I have to look at the general solution. So we got to say plus 2 pi k, and then the same thing here. All right, plus 2 pi k. Now, so now we really haven't solved it yet. Even if we were only finding a general solution, we're still not done. What do you think really needs, what else needs to happen? Right, you need to divide the 2, so we've got to divide the 2 out. All right, so they'll give me theta equals. Now there's a trick here of dividing a fraction by 2. Think of it, instead of dividing a fraction by 2, it would be multiplying by 1 over 2. So it just basically takes the denominator and multiplies it by 2, or doubles it, yeah. Okay, so whatever number was right here, we would multiply it by this number. So that would be 2 pi over 6, which would be pi over 3. All right, and then plus now what these 2's would cancel. All right, so it'd just be pi k. All right, and same thing over here. Okay, it's just different numbers over here. So this would be theta equals, now this would be 4 pi over 6, should be 2 pi over 3. Okay, plus pi k. Now, those, again, are my general solutions. Now, here's the thing. This problem is not asking for the general solutions. It's only asking for the solutions that go between 0 and 2 pi. Uh-huh. So then it would have just been pi over 2k. Okay, does that make sense? Pi over 2k. If it would have been tangent, because you wouldn't have the 2 here, would you? And the 2's wouldn't have canceled. So it would have been pi over 2k. All right. Now, so here's what we have to do. We've got to find the solutions that fall. So what we're going to do is come up with values of k. Now, if I let k be a negative number, that's just going to turn it to negative, isn't it? Okay. And so we only want from 0 to pi. So we don't need k to be a negative. So we need to be k to be 0 and the positive numbers. Okay. So we're going to do this. All right. What if k is 0? What would the solutions be then? So we take 0 and we just plug it in for k. Now, if we plug in 0 for k, this would all just turn into 0. So the solution would just be pi over 3. Okay? Same thing would happen here. If I plugged in 0 for k there, this would just be 2 pi over 3. All right, so plugging in zeros, pretty simple. Now, so what would my next iteration of k be? 1. So we need to let k equal 1. And so what we're going to do is we're just going to keep building, but we can't go on forever. We're going to stop when, you think? Right. When it gets bigger than 2 pi, we're going to stop. Okay? Now, so let's see what happens when k is 1. Maybe 1's too big. Okay? So we're going to put in 1 here. Now, this is going to require a little bit of thinking here. So we'll do pi over 3 plus, now if k is 1, it would just be what there, pi, right? Now, how can I add pi over 3 and pi? I got to get a common denominator. So we can write this one as 3 pi over 3. So we have pi over 3 plus 3 pi over 3. And so that would be 4 pi over 3. All right. Now, let's do it to our other one over here. Let's let k be 1 there. So that would be 2 pi over 3. Now, let's take a shortcut here. Instead of saying, well, pi times 1 is pi, let's just go ahead and say 3 pi over 3, because we know we're going to have to do that, right? And so that would be 5 pi over 3. Okay? Now, look what's going to happen if k is 2. If k is 2, this is going to be 2 pi, isn't it, right here and right here. If I add pi over 3 to 2 pi, I don't know what it's going to be, but it's going to be more than 2 pi, isn't it? And what? We can only go up to 0 to 2 pi is what the directions say. All right, so that's it. So now let's circle the solutions. All right, what? Pi over 3 and 2 pi over 3. What else, though? You have 4 pi over 3 and 5 pi over 3. So these coefficients end up having a little bit more on their solution. So you see how it really wasn't that difficult, but it's definitely, yeah, it's long.